Welcome back for the fifth installment, the fifth lecture in our series. For those of you who've been here the whole time, of course, we started off with an overview of the future of the American space program and where we're going. Then we followed that up with our 2 lectures about our transportation system, which is what we're working on right now. We have money to do that and funding to do that, and that's happening today across the country. And then last week we talked to you about one of the 2 really tough problems, I sometimes say miracles, that have to happen for us to pull this off, and that was landing human-scale payloads on the surface of Mars through the really poor atmosphere that Mars has. And today we're going to hear from Dave Moore and Martha Cloudsley about how we're going to attack the problem of the effects of radiation on astronauts. So it's a long trip to Mars, and Mars doesn't have the same protections that we enjoy here on Earth from our magnetic field. And so we have to come up with ways to protect astronauts on the way and while they live on the surface of Mars. And you got two of the best experts here this morning, and I'm going to turn it over to them.
Thank you. Can y'all hear me? Okay, good. As Steve mentioned, we're going to give you all a briefing on the radiation protection efforts that we're ongoing now over at NASA. As most of y'all are aware, the effects of radiation here on Earth, how it can affect our power grids, our water system, our cell phone service, our airline industry. But as we move further away from the Earth's protective magnetic field, there's issues with protecting the astronauts and their safety. And as Steve mentioned, we're looking at missions that could go anywhere from 2 to 3 years. So we're working on processes and to protect the astronauts going forward. Okay, thank you. All right. As Steve also hit on, I guess we're the 5th in the installment, and you guys have probably already seen our flow chart, how we propose to get to Mars. And what I want you to take away here over in the far right, you see our missions, 2 to 3 years. So we have a big effort ongoing in the agency to address that the top pole problem with space radiation. To give you a kind of perspective of what prior astronauts have seen for exposure in space, you can see on the graph here of the other human missions, of the Mercuries and the Geminis. And what I want you to focus on is over on the right, you see the Mars, the little box over from Mars. We're looking at this exposure that we're expecting the astronauts to see is a factor of 10 greater than what anybody's ever received currently and flown. So this is a big problem for us, and we're spending a lot of effort trying to address it. To give you another perspective and put it in context of what we see here on Earth, you start on the line there, the log line. You see over here in the far left, if you go get an office visit, you get a chest X-ray or mammogram, the kind of exposure you get. And then as we move further to the right, you see commercial airline pilots. You'll see it maybe a factor of 10 greater exposure. And then as we move one step further over into the ISS realm, the astronauts there are seeing like 1,000 times greater than what we see here on Earth. But then if you move over where we're proposing to go, Mars, in a 3-year mission, we're seeing something like 10,000 times greater than what we currently see here on Earth. We're very blessed to have the Earth shielding, protecting us, magnetic fields. I'm going to turn it over now to Martha, and she's going to give you a briefing on the environments that the astronauts are subject to and some of the risks that they have to endure, and then she'll turn it back over to me, and I'll give you a briefing on some of the mitigation efforts that we're doing here at Langley. There you go.
So I'm going to try in a very few minutes to explain why we're worried about space radiation. There's really 3 types of environments we're worried about. There's galactic cosmic rays, which are heavy ions that are out there all the time. There's solar particle events, which are isolated events but can provide a very large dose. And then there's radiation that's trapped in the Earth's geomagnetic fields. And we're going to talk a little bit more about each of those. Galactic cosmic rays are highly charged energetic nuclei that enter our solar system from outside the solar system. It's modulated by the solar wind. So we have an 11-year solar cycle, and it'll go from more intense to less intense, but it's always there. It's about a factor of 2. It varies from solar max to solar min. The galactic cosmic rays, it ranges from protons all the way up to much heavier ions like carbon, aluminum, gold, iron. And there's a huge range in energy from just a few eV to tens of GeV. So, you know, the heavier, the faster ones are moving at speed of light and just very, very penetrating. So that's our problem. So you don't get enough dose from galactic cosmic rays to worry about it for short missions. So it was never a problem for the Apollo missions. You know, they were there for a few days, didn't get enough exposure. But for these longer duration missions, you're getting enough dose, so we're worrying about increased risk of cancer especially. So it becomes a shielding problem for the 3-year Mars mission. Is something we just can't actually close on it. We can't provide enough protection right now. Question?
Do these rays, they affect the DNA? They can bring change?
Yes, yeah, and we're going to talk a little bit more about that in a few slides. But the question was, do the rays, can they affect the human DNA? Would they break the DNA strand? And the answer is yes. So solar particle events, unlike the galactic cosmic ray environment, which is always there, solar particle events are isolated events. They correspond to coronal mass ejections from the sun, though the way they relate is not always intuitive. So you can have a big coronal mass ejection and not have a big solar particle event, or vice versa. So it's really hard to predict, and Dave's going to talk a little more about that in a bit. Really large events that would provide significant risk to astronauts are pretty rare. We see 1 or 2 for 11-year cycle. But a large event that caught astronauts on EVA without protection, on spacewalks, would be a challenge. It could be a real health risk. So the one thing that's good about solar particle events is that it's mostly protons. And they range in energy, again, from a few eV this time to about 1,000 MeV. So they don't go quite as high as the GCR. Shielding is much more effective for them. So the point is that we have to get astronauts in a place where they're shielded. It's a solvable problem, but we need to make sure that we address it. And trapped radiation, we're not going to talk a whole lot about that because we're mostly focusing on exploration missions that go beyond the Earth's magnetic field. We're mostly worried about that mission to Mars. So. But I did want to mention it because it is another source of space radiation and one that astronauts have been exposed to. What happens is that protons and electrons especially, and a few other particles, but mostly protons and electrons, get trapped in the Earth's magnetic field lines. And they swirl around the field lines, and they just follow the field lines back from pole to pole, and they're always there. The space station is at a pretty low orbit, so it doesn't go through the worst of the Van Allen belts, which is why the astronauts are relatively safe. It does sort of pass through them on each rotation, and you get a proton dose as that happens. So they do get some dose from this. The magnetic fields also provide protection to us on Earth and to the astronauts on ISS. The lower energy galactic cosmic ray particles are actually, their path gets deterred. So they provide a lot of protection to Earth. Okay, just backing up, what are these charged ions we're talking about? And for those of you who remember your high school chemistry class, this picture might look familiar. So just remember what an atom is. An atom is basically a nucleus surrounded by electrons. Now this picture is not at all to scale. Okay, the entire atom is about 10,000 times bigger than the nucleus. So most of the volume of the atom is the electrons rotating, and the nucleus is very small and very, very tightly packed. Now the electrons are negatively charged, and you have an equal number of positively charged protons in the nucleus, and those are bound together with neutrally charged neutrons. So the nucleus is made up of neutrons and protons packed tightly together, and then you've got orbiting electrons. So when we talk about how shielding works, picture your aluminum wall, which is between the astronauts, and yeah, this is a really old graphic, I know, but the astronauts are on the inside of the vehicle. The space radiation environment starts out on the outside of the environment. You get tightly packed nucleus of protons and protons and neutrons, which impact the wall. Now the wall, again, most of the volume is those electrons, and then every so often on a very miniature scale, you have a nucleus. So mostly what happens is these particles moving through the wall, they're positively charged because they've been stripped of all their electrons, so they're trying to grab an electron from the atoms making up the shielding wall, and it slows down as they do that. So the particles coming in are slowing down, and then every so often they bump into a nucleus of the shielding wall, aluminum or whatever it is, and they'll break up, and secondary particles will be produced. It is possible that the environment behind the shielding will be worse than the environment outside the shielding. If you picture some heavy ions here, and they come through the shielding, and now you've got protons and neutrons being produced and more particles being produced. So we have to be really careful in how we work shielding that we don't actually make it worse. Permissible exposure limits. How much radiation are the astronauts allowed to get? We have several kinds of limits. We have 30-day limits. 30-day limits are basically a threshold value. You don't want to get more than this amount of radiation to avoid things like radiation sickness. And it's basically what you're worried about is the astronaut being on a spacewalk when a solar particle event happens. As long as they get to protection before the solar particle event happens, the 30-day limits don't come into play. We also have career limits for some specific effects, circulatory system, central nervous system. We're not going to talk a lot about those. The big challenge for us is this requirement that risk of exposure-induced death be less than 3%, and that we ensure that at a 95% confidence level. We're going to talk more about why that 95% confidence level statement is there. But what this means is, we all have a risk of dying of cancer. The astronauts' risk of dying of cancer due to the exposure they're getting should be no more than 3% more than average Joe Americans. The other thing is radiation exposure should be kept as low as reasonably achievable, and this is the Alera principle, and it sounds like really squishy words. You guys go, do the best you can, okay, but it's actually a really important requirement, because what this requires is that every time we send an astronaut in space, we need to do all of the trade studies to ensure that we've done everything we can to keep them safe. So you need to look at your vehicle, and is there a way you can redesign it, and evaluate each possible way you can redefine it. You need to look at your mission ops plan for when they're going to be doing spacewalks, and basically test each one and figure out what's the best way to keep the radiation exposure as low as reasonably achievable. It's a very important requirement for us. So again, why are we so worried about this space radiation environment, and why do we have this ensured at a 95% confidence requirement? So the space radiation, as we said, it's protons, but it's also heavier ions, and it's basically different than anything that humans have been exposed to. We have a very limited number of astronauts that have had some extensive time on ISS that have been exposed to a somewhat similar environment. But the low-energy particles are pretty much cut off at ISS because the magnetic field protects them. So we don't have any population of humans that have been exposed to a lot of heavy ions. There's no way for that to happen on Earth. So most of our risk estimates are based on atomic bomb survivor data. So we're extrapolating from a totally different type of radiation and a totally different population with a totally different diet than people were eating back then. So there's a lot of extrapolating going on. If you look at this picture on the right, which might be a little bit confusing, what this is the path of different types of particles through a material. Hydrogen protons are on the left, helium are just a little bit heavier, and then as you move to the right, it gets heavier and heavier all the way over to iron ions. This is sort of the path they carve through the material. So the iron is bigger, it's basically just clearing a bigger path, so would be causing more damage to your DNA. And it's shooting off more delta rays, the sort of the scattered look, or delta rays coming off the particle, which also can cause damage. So again, the problem is that we haven't had humans exposed to this, so how do we estimate their risk? Even if we can calculate perfectly how much radiation they're seeing, how do we estimate their risk? And the way we're working this is by doing more and more animal testing in heavy ion beams, but it takes time. So your question about DNA. These are just, diagrams. Here's an intact DNA strand. And up here you see, if an X-ray would come through, it might be able to do damage to one very, very small part of that DNA strand. However, a heavy ion has the ability to break both strands of the DNA, and it's shooting off delta particles which are doing more damage. So a heavy ion has the ability to affect this DNA strand so that it can't repair itself, which actually wouldn't be the worst thing. If the DNA, if you kill a few cells, we've got lots of cells. It's when they repair themselves in a bad way that we end up with cancer. So there's three things that can happen. You can have a single strand break where a particle goes through one strand of the DNA, and those sometimes repair themselves correctly. You can have a double strand break, and this is a problem because they can come back together the wrong way, and now you've got a mutated cell, and if that mutated cell propagates, at some point you've got cancer. Or you can have chemical changes to the DNA. All of these are big worries, but the double strand breaks that you see with heavy ions is really our greatest concern. Okay, so how do we calculate astronaut risk? There's a bunch of different parts that go into that. We have to be able to evaluate the space radiation environment, and I showed you plots of what the GCR environment looks like. We actually have a pretty good fix on that. It's not perfect on any given day, but we have a pretty good fix on what types of particles are there and what energies are there. We need a radiation transport code to calculate how that environment changes as it goes through aluminum shielding or whatever kind of shielding, and as it goes through human tissue. I mean, your body is providing shielding to your internal organs. We need models of the shielding. We need models of the vehicle. We need models of the human body. All of those things have some error associated with them in the way we do it now. It's small, but we don't have it perfect. Okay. Once you've done that, though, and you actually know the exact radiation that's being absorbed by your liver and by all of your internal organs, we need to be able to figure out what biological risk that poses. So we need radiation quality factors that take into account the fact that one type of particle is much more damaging to humans than another. We need tissue weighting factors which take into account the fact that one type of tissue is much more sensitive to radiation. You're much more likely to get one kind of cancer than another. And we need radiation coefficient factors to convert to risk, and we need dose and dose rate reduction factors. When we test things in the lab, we give it a lot of dose really quickly, whereas the GCR environment, as I said, you have to be out there for quite a while before it becomes a problem. It's a much more slow dose that you're getting. All of these, we have significant uncertainty with those. So there's our problem. If we don't know really reliably what that quality factor is, how do we tell the astronauts what their risk is? And that's where that requirement that we ensure that astronauts get no more than a 3% risk of exposure-induced death is ensured at 95% confidence. This probability distribution function may or may not be confusing looking, but the red line could represent our best guess at the astronaut's risk. So you take the best environment model we can come up with, you use the best transport codes, you use the best models for the vehicle, you calculate the organ doses, you convert that to risk using the best quality factors you have. However, if the quality factor is a little higher, this is another estimate. If the quality factor is a little lower, this is another. If the dose rate factor is a little higher. So all of these black lines represent possible answers for the same exact mission. How much risk is the astronaut really seeing? So if we want to ensure that the astronaut has no more than a 3% risk of exposure-induced death at a 95% confidence, we have to provide shielding that gets us way over here on this plot. And that's where we end up with a mission that doesn't close. We don't know how to provide that much protection for a 3-year mission to Mars, and it's something we're still all actively working on as fast as we can. So let's talk about shielding materials. Most vehicles are made out of some sort of aluminum alloy, though there's a lot of plastics involved in current vehicles, in the internal structure and of course the things you bring, food, water. But anyway, aluminum is not a great shielding material. These plots are effective dose to the astronaut versus shield thickness. So you can see you're getting a much greater reduction in materials that have a hydrogen content. Polyethylene, water, pure hydrogen would be even better, but it's really hard to build a vehicle out of pure hydrogen. Anyway, so one thing to note is that materials with hydrogen provide better shielding for the same amount of mass. So when we can, we want to use those types of materials. The other thing to note from this plot is, on the left you've got one for galactic cosmic rays, and on the right you've got one for solar particle events. The plot on the right, this is a log scale. So as we said before, shielding solar particle events is much more effective. You're getting a significant reduction in dose here by adding a little bit of shielding. Over here you're getting much less reduction in dose by adding shielding. So we can pretty much shield SPEs, we just need to make sure it happens. Galactic cosmic rays is a whole other issue. The other thing to see about these two plots is that the plots are leveling off. Add a little bit of shielding, you're getting a good amount of reduction. Then you keep adding more and more shielding and you're getting a lot less bang for your buck. And I know you've heard the previous speakers talk about how launching every pound is a problem. The goal is absolutely to minimize mass. And here we're adding more and more mass and getting very little reduction in dose. So that's our problem, that's our challenge. Here's some calculations for how many safe days in space astronauts have before they reach that 3% risk of exposure-induced death, calculated at 95% confidence. And there's some assumptions that went with this calculation. If you had different assumptions, you'd get slightly different numbers, but it gives you a real feel for it. In this case, the astronauts were in a 20 gram per centimeter squared aluminum vehicle. So think Mork's egg. It was just a spherical vehicle for these calculations. Two things to note. Well, the big one is that no matter what assumptions you make and which astronaut you send, we're looking at less than a year before they reach that 3% risk of exposure-induced death with the 95% confidence. Okay. The other thing to note is that males can stay longer before they reach it, and that younger people, females or males, can stay longer than older people. The other way around. Older people can stay younger people have greater risk. Excuse me. So right now, this is the NASA model, the 2012 model. So these are the numbers you would use. The right-hand column is a new model that people are looking at. Basically our astronaut population is a very healthy group of people. If we assume that none of them have ever smoked, which is a pretty close to real assumption, they have a lower risk of cancer, so they could maybe stay a few more days. But none of these models are showing that you can stay for 3 years. So again, this is our problem. So what are we going to do about the problem? Well, basically, we're going to attack it from every angle we can. And what's not shown on here, but was mentioned at last week's meeting for those of you who are here, so I want to bring it up, the absolute best thing we can do is get there faster. Astronauts stay a shorter amount of time, they get less radiation exposure, they have less risk. So if there's a propulsion breakthrough that allows us to go to the Mars and back faster, that is the best answer. And I don't have that on these charts because those of us in the radiation community aren't really working that part of the problem. So there are 4 ways that we can attack it. The first is radiobiology and biological countermeasures. Reducing that uncertainty will definitely help. You saw how much of an effect that has. And if we can find some way to give astronaut medications or find some way to help with that radiation, that will be great too. Forecasting and detection. We got to make sure those astronauts get into shelters the minute the SBEs are happening. Shielding materials and configuring vehicles better is a big part of it. And there's a possibility that active shielding will be part of our solution. So we're just working them all at the same time and trying to together come up with a solution that works. I'm going to talk about the radiobiology and biological countermeasures briefly and then hand back off to Dave. So as we showed on our probability distribution function, we've got about a 450% uncertainty associated with astronaut cancer risk. So if we can reduce that, possibly they can get more dose and still stay under that 3% risk of exposure-induced death. So that is really a big, big part of our goal. We have current models showing, our current models completely rely on atomic bomb survivor data, and that's a problem. We need more data related to heavy ions. We have some evidence that heavy ions have a different effect on humans. We're seeing earlier tumor growth and more aggressive tumor growth in animals that have been exposed to heavy ions. So this is something we're really worried about, and NASA does support an extensive biological experiment program. Okay, as far as radioprotectors and mitigators, this work is really in its infancy. And if we had this all pinned down, we would have solved the cancer problem. You know, the NIH could come to us, we could tell them how to solve it. So it is a really challenging problem, but it is being worked. A couple of focuses, they're looking at biomarkers that would predict radiation diseases earlier, so then we could get people to treatment earlier, which might reduce the chance of dying of cancer. Hopefully this will allow us to get earlier treatment, and it may, in the future, allow us to actually do personal risk assessments. So instead of talking about female astronauts that are 35 years old as compared to female astronauts that are 45 years old, we can talk about astronaut Dave Moore and, you know, have a complete model of Dave Moore's body and a complete model of Dave Moore's risk that includes all of his risk factors from his previous life experience. That's a long way off, but that is the goal. So just one picture, we're really proud of our space radiation laboratory up at NSRL. This is, it's a laboratory at Brookhaven National Lab, so we basically partner with them. We use their beam lines, but we have our own facility on their center. Brookhaven is a Department of Energy facility. So this is the beam line. You basically accelerate particles faster and faster, and then it comes shooting down the line into our facility. And we can put cell cultures in the line, we can put small animals in the line. The problem is it's a slow process. You saw the galactic cosmic ray environment is all kinds of different particles at all different energies. You've got to do one particle and one energy at a time here. So it's a big challenging problem, but we're working it. And I'm going to pass off to Dave, who's going to talk about the engineering approaches. Questions? It's different ions. You have the same type of problem where you're extrapolating from a different, the question was, what about data from Chernobyl and the Japanese meltdown and 3 Mile Island? Don't we have some more data other than just atomic bomb survivor data? And the answer is you've got the same problem with Chernobyl where it's a different type of radiation. You also have much smaller populations, especially with the Japanese situation. So we don't have a whole lot of data to build models on. You had a question? It means creating a magnetic field, and Dave will talk a little bit more about that. Okay. The question was, what is active shielding? And the answer is Dave's going to talk about it. Okay. Question? I don't know the answer to that. We do know that there is significant bone density loss for missions, and I don't know where we are currently with studies about 3-year missions, and so I can't answer that one. Question?
With the astronaut's medical history of his tendency towards cancer enrich with it all?
Question is, with the astronaut's medical history, would his or her tendency to get cancer enter into it at all? Right now, we keep track of all of their previous exposures because we have many astronauts who go up more than once, and that does enter into it. They use that to decide whether they can fly again. We do not have, we do not use specific, your type of group is more likely to get cancer than some other group. We don't, we had some evidence that women were more susceptible than men. We don't use that in deciding who gets to go at this point. There's research looking at that, but we don't use that as a qualifying or disqualifying factor. And as far as specifically whose risk, how much risk individuals have, we're really not there with the science to be able to predict, my risk being more or less than Dave's. Okay. Question? Delta radiation. I'm not sure I'm going to do a good job explaining it. As the particle goes through, it's basically delta rays are emitting energy. So you're passing near a nucleus, and it's having an interaction that's causing that particle that's coming through to shoot off a delta ray. Yes, yeah. Sorry, I'm not doing a great job explaining that, but that's, okay.
Let's see if they clap when I'm finished. All right. Another area we're working on integrated approach is forecasting and detection. It's pretty. I'm sorry. Yeah. If you can forecast the occurrence of the event, that gives your astronauts that much more warning, that much more time to go seek shelter, especially when an SPE is occurring. And then also, we're working on capabilities to improve our detection possibilities, and I'll show you here. In the area of space weather forecasting, there's a lot of research and models being done that have work on addressing the issue of forecasting and arrival time, when the event will actually hit you, and then what that dose will be and how long that event will occur. But that's all been, up to the last few years, been kind of researchy. But we've got an effort ongoing now at Langley to integrate that work into an operationals platform where we can have the console operators on the ground or the astronauts actually in space have all this capability and knowledge right in front of a screen for them. It's a suite of software we put together. As you can see on the graphic on the left, it kind of gives them a stoplight chart. Red, green, or red's bad, green's good. It can give them other features where they can go in and check on the duration of the event, when it's going to arrive, how it compares to other historical events that we've recorded data on. So this is some work that we're doing in the area of space weather. Just to go dig a little deeper in the all-clear forecasting area, we're hoping to increase our warning time capability. Current state of the art is an hour or so. We're hoping to expand that from 4 to a 24-hour window, and we're doing that in partnership with our NOAA. And the idea here, like I mentioned prior, was to give the astronauts more time to seek shelter. But also this helps in the operations planning. Say you need to go outside your habitat to do some maintenance or whatever. If you know that day is going to be a good day to go out and do an EVA, this is ideal for you. The operators on the ground can plan the mission for the astronauts. What you see on the graphic on the right is an image of the sun. We have numerous assets, circling the sun, recording data, measuring, seeing activity, and working with our partners at NOAA, we can identify the active regions, and then we take this data, run it through our analysis codes, and make these forecast predictions. And area of arrival times, we're again working with NOAA. In this area, we're making use of terrestrial weather. What we currently do, everybody here is familiar with the hurricane forecasting. You've seen it all on the news and TV. Well, we're following the same type of logic and process. With modern computers, you can now do massive amounts of simulations in a short period of time, and you play with many variables, and it'll help you, idealize when that event will hit you and occur. And you can see on the graph on the left there, it's sort of like tracking a hurricane. As the event gets closer to land, our prediction capabilities are better, but as we extend further out, our uncertainties grow. But we're working to minimize that, and I think you get that time there. I mean, if we can increase that arrival time estimate, that gives that astronaut just more time to seek shelter. All right, in the area of environmental monitoring, we've got quite a bit of work going on there too now. And what you see here is a REM, a Radiation Environmental Monitor. This is actually flying on ISS. We've, in a prior, I guess this too is new technology within the last few years. We've been able to miniaturize it. Before it was more bread box size and mailbox, and now we've been able, with modern improvements in computer power, been able to bring it down into a thumb drive size. So what you see here in the graphics is the thumb drive inserted into a portable laptop, and you see the astronaut inside one of the U.S. labs up on the ISS. This capability, as it progresses, will have these, we were forecasting, we'll have these embedded inside the structure of the habitat itself. So it'll be real-time monitoring. This gives it's just another way to give the astronaut an indication of what the exposure is he's currently seeing, and maybe some warnings that, hey, things aren't going well, so you go seek shelter. in the area of particle spectrometers, it's another detector. We just recently, I think y'all probably aware, we flew the Curiosity rover that's currently up on Mars. Well, this piece of detector equipment was embedded inside the rover. And so this gives us real-time estimates of what the radiation environment is on Mars. But also this provided us data on a transit to Mars, a flight, leaving Earth and taking the 6 to 9 months it takes to get to Mars. This gave us a good understanding of what we would see, how many SPEs would occur, and what the daily radiation at GCR environment was. It's very low mass and low power, and it's doing a great job. I mean, we're still receiving data daily on this that the modelers on Earth can use to help improve their models. Next, we're going to talk about shielding materials, the use of passive shielding. Martha talked, showed a few charts about the different materials and which ones are better to use. So we're trying to take that knowledge and integrate it into our future habitats and how to do a better job of providing shielding on the capsules. You can see here in this graphic, everything is in play. If we can do a better job of the shell structure material, instead of aluminum, maybe some composite, would be structure. Maybe the secondary structure the same way, and also the equipment that's inside the habitat. Anything to give them more hydrogen-based shielding materials will improve the stay of the astronauts and give them that much better protection. Another area that we were looking at, is when, say, we get to Mars, maybe we can make use of the regolith, which is another fancy word for Mars dirt. Maybe we can make use of the dirt that's there, the topsoil, and take our habitat, either, you see on the right, encapsulate ourselves with, put a large amount of this around our habitat, or seek a cave or a lava tube and embed your habitat in there, and just take use of the surface protection that's available. Next, we talked about the passive materials. Now, another area in that area is configuration optimization. Maybe doing a better job of laying out your equipment, your subsystems, and around in your habitat. This is an effort that has got a lot of work that's done now. Before the habitat, let me back up here a minute. You can see on the left here the habitat focus. If we just let the designers, without a radiation perspective design it, you envision that if, they would put it ergonomically, like you'd like to set up in your office or your home. But if you you have an eccentric radiation focus, you're going to see like a little Incoon fort like you would build in your parents' living room when you were little. So there's this dynamic that's always going on amongst the designers and the analyst folks. So we've got a collaborative effort now going in the agency to work together. And so they bring in the Marthas and into the habitat design and try to see if we can do a better way of placing what we have as grow up. Along those lines, there's a effort that I oversee here at Langley for designing protection systems for SPEs. And we call this reconfigurable logistics. When you're in transit to Mars, there's no phone home or a supply ship coming right behind you. So you have to make use of everything you have on that capsule at that time. So that includes your water, your food, even your trash. I mean, everything is in play. Everything has to have a secondary purpose if you want to make use of the total mass to give you that protection. So you see over on your left slide there, just a typical cargo bag. So we worked with the people down at Johnson in operations and said, hey, how about if we add a few zippers here and have this so it unfolds and turns into a drape, a curtain, so we could mount this on one of the racks, and typical rack, and hang mass structure on there to provide shielding for the astronauts. Just something simple, but everything you got to think outside the box. And so what you see on the right here is in our labs we did a bunch of humans in the loop, human factor type analysis. It does us no good to come up with these shielding ideas and the astronauts say this is bull. This won't work. This is not this is not practical. So we do a lot of humans. Get a lot of. We bring people in the lab there, and we give them a set of instructions. We time them. We ask them about the difficulty. We do a lot of trying to figure if it's practical to do. And here, see here, I was going to say, I'll still say, this is what this is prior to me and Martha starting the task. This is what we used to look like, but much younger. Yeah. Another area we're looking at is making use of water. Water is a great shielder. Its hydrogen content is high, and so we have a lot of contingency water on the on our missions. So the idea is here, maybe we can take that water, and if we can move it from point A over to point B in a relative bit of time, we can provide that much extra protection to the astronauts. So our team, we looked at maybe we could retrofit a crew quarters. The astronauts spend a lot of time in there, they sleep in here. This is where they go to interact with their families, like their little private space. So we looked at maybe adding some water bladders and what would be entailed for plumbing, actuators and valves to move water and over and to provide that temporary shielding, with the idea that this would be temporary. It gives them the shielding till the event passes. The event can last maybe a day to a day and a half, and then we would move that water back to where it was originally supposed to be. On the area of personal protection, we really don't have a habitat concept in place yet. Everything is going that way, but we don't have a design yet. So we were looking at, well, what could we do in the meantime? So this is an area where we look at maybe this can be portable. We can go to any habitat design you come up with, but this will also be a personal wearable. So you can see over on the left the astronaut candidates wearing this little vest. The idea here is you pack this full of polyurethane or maybe water, or you can insert food, anything to give you that mask, to give you that extra protection. And sorry, was there a question? Yes, sir.
But there seems there to be no protection for one of the most important things, the brain.
Yeah, well, this one is designed to protect the vital organs. I don't.
You would probably want a helmet to go with it and protection for the lenses. But this covers where the bone marrow is most prevalent.
Yeah, we have done some work in that area of giving them a cover and all, and we have some pictures in our labs, and it's very popular on the tours. Everybody wants to get their picture made next to this, this mannequin. But yeah, we have looked at that, and it's a difficult problem. Sleeping. The astronauts, when they sleep in space, they're sleeping in what they call a sleep restraint. It's actually mounted, Velcro mounted to their sleep area, and that's so they won't float around while they're asleep. So we looked at areas where maybe we could retrofit a sleeping bag contraption that would wrap around them and tomb them, and then the same logic as the vest, pack it full of food, water, whatever to give them that extra protection. All right. Okay, I've got a movie here. I'll show you. This kind of brings everything into perspective. The prior slides I was just showing you, but I think this will help explain a lot better. I'll tell you a few things. I'll highlight a few items. Is that better? Okay. Well, here's an artist rendition of a warning. You see something occurs on the sun. It gives the astronaut a real-time, got to go seek shelter. The event is arriving, and then we transition into here where we're looking at retrofitting crew quarters. This one is the wall-to-wall design. Simple as turning a valve. In our lab, we actually have like iPads, and we do it all automated. We can move it through our suite of software. We can move the water into and out. This is on the lines of reconfigurable logistics. Moving mass that's stationed in a different part of the capsule or your habitat over into where you need it to provide you that temporary shelter. Gives you kind of an idea of what's involved to do that, because you wouldn't want this protection mass just sitting around. You want it to be portable and put away. And here's a visualization of the bags, the zipper unfolding. And what you see here in these white tiles is an effort we have going on to repurpose the trash. Currently, you have as you eat your way through the mission, you have all these byproducts the trash. So there's an effort at Johnson and Ames to compact the trash, burn it, and reprocess it, and turn it into shielding tiles. So if you get enough of these tiles, you can add enough. You can get added protection. So that's the idea. You consume it, you reprocess it, and you turn it into shielding materials. We have the astronauts here. You can see they're in close quarters. We try to double bunk them in. Because you have limited amount of mass, so you try to get them as tight as you can, so you can get as much shielding between them and the exposure as possible. So they would sit in this tomb here for a day and a half. They can go out as they need to check vital systems, but they would spend the majority of their time hunkered down in these little mini forts. Yeah, there's no gravity. Yeah. People always ask about that. Do you want to be the one on the bottom or the one on the top? Yeah. Okay. Is that a cue for me to speed up? Here's the drape idea. We take out those folding bags. They can move these drapes, mount them to where they need to mount for structure and shielding. Everything has a dual purpose. That's the takeaway here. What's that again? I'm sorry. We have times. We try to get them to do it in like 30 minutes. That's one of the rules we shoot for. 30 minutes. The question was, how quick can they build these shelters? And we target 30 minutes. Well, we take that, I don't know, have y'all ever seen space food, how it's packaged? We take that packaging and we burn it, compact it, and turn it into those protection tiles. So, yeah, so everything is reused. Yes, ma'am. All right, the last item I'm going to hit on very briefly, active shielding. That question was raised by the audience. This work is in its very infancy. There's a lot of bang for your buck if we could perfect it, but there's a lot of engineering issues we have to overcome to make it work. And some of the items are the amount of the size of the magnets, what's required, the power, the structure, how much they are, the mass, how do we mount them to our capsule structure. There's a lot of engineering issues they have to overcome. But the idea is, surround yourself create an artificial magnetic field like Earth has. And, the idea, if the radiation comes in, it's repulsed, But there's still a lot of work that needs to be done on this right now. This is more a researchy realm. All right, I think that is the... These would be electromagnets or permanent magnets? They would be permanent, yeah. Is there any questions? Yes, sir. I'll have to turn that over to Martha.
Micrometeor type protection. You mean actual pieces of... That's a whole different area. It is very important, and there's a lot of research that goes on, especially at NASA Langley, about designing shields and spacing different materials so that they slow down those type of projectiles. But that's not our area, I guess. Next.
Does Mars have a protective belt similar to our own that
No. Does Mars have its own protective belt like Earth? And then the answer is no. Yes, sir.
This is sort of a basic, and I think it's a two-part question. My experience with the medical imaging community, as in X-rays and so on, years ago, those badges, the quantic...
The dosimeters?
Yeah, the dosimeters was called Roentgens.
Mm-hmm.
That's changed now. Again, I think, I don't know what the terminology is now.
I think it's sieverts, right? Is that the...
And then, Dr. Cloudsley, you mentioned something else. You mentioned that in that's not analogous. You said that you have these high charge and energy ions which are different from X-rays and gamma rays. What's the unit of measurement? I saw a lot of scales there. What is the unit of measurement?
We still talk about astronaut dose in terms of sievert. Is that what you mean by the unit? Yeah, yeah. So dose is measured in gray, which is just energy deposited per unit mass. However, there's another unit called dose equivalent, which is measured in sieverts, which actually has a quality factor folded into it that accounts for the risk that these particles provide to humans. So two different types of particles can basically deposit the same dose but provide very different risk to humans. So we use sieverts to be a measure of how much risk the humans have.
So even though it's not analogous to the gamma ray, to the X-ray, it's still the sieverts, but there's a different component in it?
Well, sievert is how much dose equivalent astronauts are getting from any type of particle. Yes. So basically you've got X-rays and gamma rays that you talk about here on Earth. In space we have charged protons, charged helium ions, and those which are our primary concern. But we measure astronaut risk from any of them in terms of sievert. Okay. Question?
Yes, that is one of the issues that we're trying to overcome. The byproducts, the gases, the outgassing. Yes, that we are. We've done this on Earth. But it's like we before we could ever fly this on a vehicle going to Mars, we'd have to demo it in like an ISS environment. There's no way that they would let us do that. Yeah. And yes, sir.
Is there any problem of this radiation over extended period of time degrading electronics or equipment and stuff?
Yes, that's. I briefly talked about that. There's a big cost associated with rad hardening electronics and equipment, and that would be all considered in anything you fly that far away from Earth and for that amount of time. Yeah. Yes, ma'am.
It takes 3 years to get there?
No, ma'am. It takes 6 to 9 months to get there, but we just don't want to go there and get there. We want to stay there. I mean,
The whole thing is going to take?
yeah, 3 years. Yeah.
So how long are you, I guess 9 months to get there, 9 months to get back?
And maybe a year on the surface or around it. Yes. Yes.
You talked in terms of using water balloons and bladders and so on.
Mm-hmm.
And I guess maybe I'm anticipating something. I think we're talking about in the space vehicle itself. Inasmuch as earlier presentations indicated there is water on Mars, would there be any engineering projections to extract some of that water, use that in a bladder system,
Yeah.
for people that are going to be
Yeah, that would be.
in there for a while? I'm sure somebody
Yeah.
thought of that.
Yeah. Uh-huh. Yeah, the question was, can we make use of the water on the surface of Mars if there's appreciable amount of it? And the answer is yes, we would definitely want to use that. You saw the sketch I had with the Regolith. That could be some supplement. You could use water plus that. Yeah. Yeah.
Doing preliminary work on that now, maybe.
Would you? I don't.
Yeah. You also want water for the astronauts for any number of reasons that don't have to do with radiation. So there have been some engineering efforts for how you would get that water. One thing is the water's not everywhere, so you need to either plan your mission to be where the water is, or you can't rely on it as shielding. But there is work going on to utilize the water on the surface of Mars.
Yes, sir.
In the bladder system,
Uh-huh.
in what way is that water changed by the fact that it's deradiated?
I am told. Okay, I'll
Almost not at all. So you asked about damage to materials from radiation. That's a very slow process. The reason humans have so much more of a risk is because if the particle comes in and damages the DNA, and then you get a mutated cell, and that mutated cell propagates, you can have cancer. If a particle comes through and damages one hydrogen atom within the water, you have a damaged hydrogen atom, but it doesn't have a way to propagate that damage through it. So you would need way more radiation than we're seeing in space.
And I'll answer the next question before it comes. The same answer for food, right? I get asked that a lot. Yep. Yes, ma'am.
3 years is a long time.
Yes.
What provision are you making in case somebody dies during that time?
That's not an option. Failure is not an option. I don't know the answer to that one. Yeah, no, yeah. Yeah, reuse them as shielding. You get the point. Yes, sir, in the back.
Two questions. One, are there any unusual radiation events that you have detected from the sensors that are on Mars now that are feeding you information? First question.
Okay.
The second question, what about this medical attention I'm seeing on the chart? What type of medical attention are we talking about?
All right. I can answer the first question, and I'll turn the second one over. The first question was when we flew the mission to Mars with the rover. What did we see? Yeah. We saw I think we saw either 3 or 4 SPEs, the events that we can design and shield against. So that was great knowledge. I mean, we did not, that was the best we've had to date of what an actual transit to Mars would look like. So that was great knowledge. And about the medical question.
I don't really have an answer either, but so the question was, what can we do in terms of providing medical attention to help astronauts who've been exposed to radiation? And we have an ongoing research project looking at those. Again, you're sort of bordering on, can we solve, cure cancer? If we figure this out, we'll have solved lots of problems. But they're researching antioxidants, which you probably have read in any number of magazines, might improve your risk of getting cancer on Earth. But they're also looking at ways to basically tell the cell it's been damaged. So basically tell the cell to go ahead and kill itself. So rather than propagating. But all of that's really at its infancy. We're working it, but right now we don't have good countermeasures for space radiation.
Yes, ma'am. Can I give you the microphone? Audience participation.
Okay, regarding dying in space, yesterday morning I went online and logged into a website on YouTube called Ask a Mortician. It is real, it's conducted by a licensed mortician, and that was the first question that I encountered on there. And in essence, the body could be ejected into space and would be frozen. And there's a whole explanation as to orbiting and entering different gravitational fields, but should you come back to the planet Earth, the mortician said the body will enter at 17,000 plus miles per hour, and because it doesn't have a heat shield, will be super cremated when it hits our atmosphere. So, but I advise you to check into that. Ask a mortician.
Thank you. Yes. Next NASA employee. All right. Yes, sir.
Is enough known about the water on Mars to know whether it's isotopic compositions?
I don't think that we know that yet, do we? That question was, do we know the composition of the water on Mars?
I don't think we know the answer to that. I think we believe that it's similar to here on Earth. They actually have 2 kinds of ice on Mars. They have CO2 ice and they have water, H2O ice. And the H2O ice should be similar to what we have here, we think. Yeah, I don't know. I think that's what last week's presenter said, but yeah.
Any other? No. Yes, ma'am. Maven? Yep. All right, help me out, Steve. You know what's on MAVEN?
I do. MAVEN is designed to help us understand why Mars lost its atmosphere. So it's going to study the composition of the atmosphere that's being torn away from Mars all the time at this point.
Is that it? Those are some very good questions. Thank you all very much.
Yeah, those were great questions. I'm thinking about how to get you guys on our design team so that we can, I know a lot of you actually worked at NASA, so of course we want you guys back. But I hope that the last 5 weeks have given you a sense of the excitement of the space program that we could have, and given you, sort of brought you up to date on where we are. I also hope that it gave you a good sense of how hard it is to do what we're trying to do. And I think that I just want to reiterate the importance of that fact. You know, Kennedy actually said this when he kicked off the Apollo program. He said, we do this because it's hard. And it kind of sounds like a simple statement, but because of the difficulty of what we're trying to do, we are going to reap tremendous benefits across many different aspects of society, from geopolitical to economic to social benefits. And that's the payoff of what we do in the space program. And as we talked about last spring, that payoff is well over 100% and very low risk. We know from history that we get that payoff when we invest in the space program. So I hope that you've enjoyed it, and we really appreciated your interest and the questions and interacting with you over the past 5 weeks. Thank you.